Hi, N4HNH here. One of the Patreon supporters of this channel asked if I would cover basic antenna theory. So let's dive right in, okay? We have a transmitter, that's our radio. It puts out power, we call watts. Now, let's talk about that for a second. Power, P, there's a formula that we've had to learn for our test, right? Power equals E for electromotive force, voltage, times I for current. So voltage times current produces power, which we measure in watts. So, we will say our radio is putting out 100 watts, but really it's putting out a voltage that is producing a current. And when you multiply the voltage times the current, or by the way, current times voltage, it will give you the amount of power that's being produced by your radio. Okay, so, voltage is potential. For the reason we call it potential is it means it represents the potential to move electrons in a conductor, literally ripping them out of the outer shell, the valence ring of an atom, okay? So, just know that what's really happening on our feed line, these two lines here, we'll say that's our feed line, could be coax, could be ladder line, what have you. Parallel wires, are typically ladder line. And they'll have, the little things holding them together, keeping them at the same distance. So, but that's a feed line. All right, so what goes into the feed line is actually voltage, which produces a current, and the amount of that can be measured as watts. Now, why does our feed line not act as an antenna? Okay? Why is it that when we connect that feed line to our radio and it starts transmitting, why does the feed line not radiate the power? It's because the radio is producing alternating current, AC, okay? Not to be confused with the alternating current coming out of your wall sockets in your home, although that is alternating current, but that is a lower frequency depending upon which part of the world you're in. It could be 50 hertz, 50 cycles per second, or it could be 60 hertz. Now, what we mean by cycles per second, the sine wave, that represents alternating current, 0 degrees, 90 degrees, 270, and 360, and really it makes a complete circle or a cycle, okay? And the number of times it does this in 1 second we call frequency, and we measure that in hertz. Today, years ago, it was measured in cycles, believe it or not. It made sense, right? But in honor of Heinrich Hertz, who did a lot of research in the area of radio frequencies, to honor him, we started referring to frequency in hertz instead of cycles. So you'll hear megahertz today, where years ago you would hear megacycles. Okay, so in your wall outlet, that is only happening about 50 to 60 times per second. RF radio frequencies simply means we're up into a realm where it's happening a lot more often per second. So, for example, at 14.2 megahertz, roughly the middle of the 20-meter band, it's happening 14,200,000 times per second. That this is completing a cycle, okay? And that what's happening with that cycle in alternating current is it's going to go plus, and then it's going to go back to 0, and then minus, and back to 0. We call that a cycle. So what we mean by the plus and the minus, the voltage is going to go up and the current's going to go up. Now, they're 90 degrees out of phase, okay? Just know that. But the voltage happens and then the current follows. So we'll talk about that more in another slide. So just wanted to establish the fact that what your radio is really producing is voltage that's creating current, and then when you do the math, we get a figure that is watts. All right, but why does the coax, ladder line, whatever you're using, why does it not radiate our signal like the antenna will? And it's because as this alternating current is alternating, this, for example, just look at here. This arrow represents the direction of the electron flow on this conductor. That represents the electron flow direction on that conductor. They're always equal and opposite in current and in voltage. So they cancel one another out. Whatever the level of current is here in voltage, it's going to be the opposite over here, and so it cancels out. And we'll talk about the basic antenna. It's called a dipole. 2 poles, 2 wires. Well, how do we get a dipole? You could take your transmission line, your feed line, and strip it back and fold it out like that, and you would wind up at some point you would have a usable antenna. But we generally, we'll have a center point, a balun, or a balanced to unbalanced transformer. We call a balun. We would have that in the center, although you don't absolutely have to have a balun in certain situations. So let's just talk about a strict dipole cut for one band. The impedance at that center point, you see here I have 73 ohms. It's approximately 73 ohms. So the reason you wouldn't absolutely have to have a balun is if you were pretty precise in the measurements you made for each of the wires on each side of this dipole. Again, dipole, 2 poles. Because if you were precise enough, then the current flow in each of these is also going to be equal and, by the way, opposite. But since they're not running parallel, they create a wave that doesn't get canceled out. Now, you see here, I equals max, the middle point of the antenna here, the feed point. That is where most of the current is flowing. So it's actually true that most of your signal is coming from nearer to the middle of the antenna. So the ends, you can see here, it tapers off. The current flow begins to drop and drops to virtually zero on the ends of the wires. So that's why it's important to get at least the middle of your antenna up high. I mean, if you put the ends up high, that's also good. And with a dipole cut for a particular band, and if you get that center point and the ends up at least a half wavelength above the ground, so you do your math for a full wavelength. For example, here, look at this. Now, I've already taken into account end effect in this calculation. If you're not familiar with end effect, let me give you a quick synopsis. Our normal formula is 300 meters per second, which is 984 feet. If you're doing your calculations in America and you're using a ruler or tape measure that is in inches and feet, then we won't necessarily use the 300. We will convert it over to feet, and it's really 984. Okay, but if you take 984, multiply it times 0.95, that will give you roughly 935. It's 934.8. And what that's doing is that's adjusting your formula for end effect, realizing that electrically this wire is going to look about 5% longer than it really is. Honestly, when you put an antenna up, a dipole up, surrounding objects are going to affect your match as well. So there's always a little bit of adjustment. If you use 935 and then you give it a couple of inches of slop in there, then it's easier to trim to get it precise where you want it, like in the middle of the band, than it is to add wire. Okay, but 935 will get you pretty close, divided by the frequency in megahertz. Now, you see it says it's 65.8 feet. That's the answer to that. Well, that means that a full wave, see, this is half of a sine wave right here. This is a half wave dipole. Imagine that continues down in the negative direction. So this 65.8 foot figure represents the entire length of the wave. Half wave dipole is only going to need to be a half that, and really it's going to be 2 quarter wavelengths. So if we take that figure, divide it by 4, we get 16.5 feet. So that means that we would cut this antenna wire to 16.5 feet per side. Okay? 16.5 feet. Now again, once you get the antenna up, surrounding objects can affect it a little bit, and so you may need to trim the ends a little bit. That's why I say, make it just a little bit longer than the math says it should be, okay? Now, by the way, if you do erect the antenna as what we call a flat top, where the ends in the middle are at the same elevation, and you get it up at least 1/2 wavelength, okay? So if you take 65, really what you want to do is use the 984, okay, to get the real number. 984 divided by 14.2. That's the height. Cut that in half. Let's do the math on that. I'll pull up a calculator here. So what we would want is we would take 984 divided by 14.2, 69, almost 70 feet. Now we can divide that by 2. Higher is better, okay? But what you want to shoot for is at least, in this case, roughly 34 and a half feet, 35 feet for a 20-meter dipole. If you get the middle and the ends up at roughly 35 feet, I'll tell you what's going to happen. The antenna is going to be able to produce for you somewhat of a figure 8 pattern off the broadside of these wires. So let's say we're looking down from an airplane or a helicopter at our antenna, and the wires run this way. All right? There's the center point, and our feed line's going straight down to our radio. What the signal's going to look like coming off of this from a helicopter looking down is more like a figure 8 broadside to the wire. So you can see here, not a lot of signal here. Now I'm exaggerating this a little bit. This would be more spread out, okay? All right, but you don't get as much signal on the ends. Why? Because look, the current on the ends drops to virtually 0. So not much signal in these directions with a horizontal dipole that's at least a half wavelength above the ground. And again, this pattern assumes that there aren't objects nearby that could skew it a little bit. Metal objects, gutters, buildings, like a storage shed, things like that, that will skew it just a little bit. Yes, and again, that's why it's always good to get your antenna as high as possible. So you want to shoot for a minimum of a half wavelength above the ground beneath the antenna. And again, that dipole will give you more of a figure 8 pattern. Now, there's also something called an inverted V, where you actually intentionally droop the ends rather than putting them up at the same elevation as the center point. And what that does is that skews this pattern a little bit more, so it's more like almost like a circle. Not quite, but it's, again, surrounding objects will affect that. But when you drop those ends like that, it will skew that figure 8 pattern, and you get a little bit more even coverage. Now, this is very crude, but I want to show you a little illustration here. Here's that figure 8. When you skew it and make it a little bit more circular, you see that? You don't get quite as much distance as you did with the figure 8 in those two directions, though, right? But you get signal in those areas where you had no signal before, okay? That's very, very generalized and crude, but that's the advantage of of inverted V, if you've ever heard someone talk about an inverted V. A little bit more omnidirectional than a pure dipole. And by the way, again, this is assuming that the antenna is cut for just this band. There are multi-band antennas out there, and they have these, what we call lobes, like this figure 8. These are called lobes. And the multi-band antennas, which, is one antenna length, but it's working across multiple bands. These are different for each band. What directions you have good lobes and what directions you have nulls will vary. Okay, but back to our discussion on how do we get a signal into the air. So again, the current, you see the little arrows here, down, up, right? The light is when this side is positive. The darker blue is when this side is positive, so it's going back and forth, back and forth. Imagine being those electrons being pushed back and forth, pulled toward the plus, but then the plus switches over to here, and then they go back here, and then the plus switches over here, and they go back in that direction. And again, chain reaction. It must be frustrating for the little electron. All right, but again, the idea is to get these two sides cut to approximately a quarter wavelength per side. Now, our coax is generally 50 ohm impedance, and the antenna feed point is 73, right? The output of the radio is 50 ohms. In order to transfer all of the power from the radio into the feed line needs to be 50 ohms as well. And ideally, the antenna would be 50 ohms. A dipole is not exactly 50 ohms. It's approximately 73. So look up here. The antenna is 73 ohms. The coax is 50. That is approximately a 1.5 to 1 standing wave ratio. That's actually considered acceptable. If you can get a 1.5 or less, go with it. You're absolutely fine with that. But that's the characteristic impedance of a dipole. 2 wires, 2 poles and then the feed line is not going to radiate because the currents are equal in opposite directions on it. All right, that's how the radio wave sets up. It just, in this case, they're not canceling one another out, and we get this half wave off the 2/4 wavelength pieces of wire. All right, so let's move along to the next slide. This one I want to discuss safety here. That's the real purpose of this slide. Remember, the current is at a maximum in the middle, so you get more of a wave, more signal strength here in the middle of the antenna at the feed point. The voltage here on the blue line, that is at a minimum there. But watch what happens out on the ends. Remember, the current goes to virtually zero. The voltage is the highest on the end, so the ends are dangerous. This could electrocute. Really, it causes an RF burn. I've had that a few times, and it's not pleasant. The 90 degrees, well, what's happening is, if you see here, the voltage is at zero here and maximum here. The current is at maximum here and zero here, and that is, if you think about it, that distance there represents 90 degrees of the sine wave. Okay? So what's happening is the voltage is at a maximum on the end of the wire where the current is at a minimum. So that could shock someone. So what my advice to you is, if you're doing a horizontal dipole, it's usually no problem because you're going to try to get that thing up, a half wavelength above the ground. With an inverted V, you're going to droop the ends. You're going to let them slope. And ideally, by the way, you want to be sloping somewhere between 90 and 120 degrees at the apex up here at the midpoint. You want that angle to be between 90 and 120. But I will tell you, you can get outside of those boundaries a little bit and it'll still function. But at the ends, you don't want to let those ends get close enough to the ground that someone could touch them because they could get injured. And so my general rule is try to get them about 10 feet above the ground, at least 8 feet above the ground on the inverted V, and achieve that 90 to 120 degree angle at the apex. So you remember with an inverted V, if your antenna is going to be more like this. So there's the feed line going up to the middle, and here are the ends. You want these ends to be at least 10 feet off the ground, just for safety's sake, so a tall person couldn't reach up there with a fingertip and touch it. Somebody going through your backyard, even if they're trespassing and see that, they might get curious, and there you are in the shack transmitting. So just know that those ends of your antenna are high voltage, and they could hurt. Imagine if you're producing 1,500 watts from this radio, the amount of voltage that would be present on the end of that wire. And so let's recap right quick. The reason our feed line does not radiate is because the current and voltage is always equal in opposite polarity, and they cancel one another out. All right? Otherwise, these waves of force here would radiate off these wires. They do, but they cancel one another out. And again, what we're really outputting is voltage that creates current, and then we measure the result of that in watts. P for watts, E for voltage, electromotive force, and I for current. All right, and our signal is alternating current. So again, here in this example, I'm alternating current. My alternating current frequency is 14.2 megahertz, 14,200,000 times per second it is cycling. These electrons are going back and forth at a blazing rate, all right? But they still cancel one another out until they get out here and the open circuit is no longer there. It now has a wire to travel into, and they are not parallel anymore, so they're not equal and opposite, and it sets up this wave. The wave is the strongest in the middle, so you get the middle of your antenna should be at the highest point. If you're going to do an inverted V, just get the middle up as at least a half wavelength above the ground beneath the antenna. And again, remember the feed point impedance, approximately 73 ohms. With 50 ohm coax, you will have a 1.5 to 1 SWR, and that is plenty good for amateur radio. All right, and again, the math, remember, I'm using 935 instead of 984 to get my antenna wire lengths so I can know what length for each side of the dipole. And essentially, you take the result of this, divide it by 4, and that tells you how long to cut each of these. And remember, you're going to cut them just a little bit long, and maybe an inch or two, and then check your SWR. If you're really wanting to be, at the lowest SWR at 14.2 megahertz, and you cut it a little bit long, you may be the lowest SWR is at 14.15 megahertz. Just trim a little bit off each side. By the way, make sure you trim it equal on each side. And if you get that close, you might want to just trim in half-inch increments, okay? And then finally, there's the safety aspect of this. Remember, the voltage is the highest on the ends, and that could hurt someone. So just be mindful of that when you install your antenna. Okay, I hope you found that helpful and informative. And hey, I want to thank my Patreon who suggested this video. And I really appreciate all of my Patreons. Speaking of Patreon supporters, I want to name a few names here. These are some of the newest Patreons who have joined as a supporter of this channel. We have Andrew, Dennis, Daniel, Scott, William, Harold, and Alex. I do appreciate your support. There's a time commitment to doing this and some expense. And so your monthly donations, help offset some of the cost, and it motivates me to continue doing this. So if you appreciate the video content of this channel, please consider becoming a supporter. There are 3 different levels of support via Patreon. There's the associate level for $5 a month. There's the executive level at $10 a month, and then VIP at $20 per month. And every little bit helps, believe me. But for the executives and the VIPs, there are some perks. There are some documents and other content up there that you might find helpful. I'll mention a couple. There's the glossary of amateur radio terminology. It covers a lot of the terms that you'll hear thrown around when hams are having a conversation. It covers the Q signals and what they mean, and gets into the various controls on your radios, the buttons and knobs on a modern transceiver, and gives a brief definition of what each of those is for. So that would be something that executives and VIPs would have access to. And if you happen to be into portable operation, I created something called a SOTA primer, Summits on the Air, where we climb mountaintops and make contacts, and it's a point system and you get awards. I created the SOTA primer. It serves as a type of quick start guide to help you get into Summits on the Air. It gives you some insight into how to get set up with that. So those are just a couple of the items available exclusively to executive level and VIP level Patreons. So if you would like to become a Patreon supporter of this channel and help me continue this mission, go to www.patreon.com/N4HNH. That's Patreon, patreon.com/N4HNH. And you'll see the 3 different levels. And, whichever one you're comfortable with, please consider supporting the channel. And of course, it costs you nothing to like this video and subscribe to the channel, which also helps our standing with YouTube. May drive some more traffic this way. We can grow the channel, and my hope is to grow the channel to the point where not only do we have some influence over the manufacturers, but maybe they'll even come to us and ask our opinion of things that they might be considering in a future product. So there's strength in numbers. Hopefully we can become influential in that respect. And if you do decide to subscribe to the channel, be sure to click the bell so you are notified each time I upload a new video. Okay, hey, thanks for watching, and 73 from N4HNH.